Text Analytics: Practical Steps to Sort Data. Written by David Feldspar. Narrated by Jason R. Gray. Introduction. Text analytics is the process of drawing meaning out of written communication. In a customer experience context, text analytics means examining text that was written by or about customers. You find patterns and topics of interest and then take practical action based on what you learn. Text analytics can be performed manually, but it is an inefficient process. Therefore, text analytics software has been created that uses text mining and natural language processing algorithms to find meaning in huge amounts of text. Why do you need text analytics? Emails, online reviews, tweets, call center agent notes, survey results, and other types of written feedback all hold insight into your customers. There is also a wealth of information on recorded interactions that can easily be turned into text. Text analytics is the way to unlock the meaning from all of this unstructured text. It lets you uncover patterns and themes so you know what customers are thinking about. It reveals their wants and needs. In addition, text analytics software can provide an early warning of trouble because it shows what customers are complaining about. Using text analytics tools gives you valuable information from data that isn't easily quantified in any other way. It turns the unstructured thoughts of customers into structured data that can be used by the business. Sentiment analysis. Speaking of feeling, our sentiment analysis feature will show you exactly how consumers feel about their subject of discussion. Our sentiment analysis is the most powerful, accurate, and reliable in the business. Beyond telling you whether a given document of text is positive, negative, or neutral, we assign a specific score to show you just how strong that sentiment is. What's more, we attach sentiment scores to entities, themes, facets, in addition to showing a general document sentiment score. This multi-level analysis can be configured and optimized to match your individual needs. Factor analysis. What is factor analysis? Factor analysis is a way to take a mass of data and shrinking it to a smaller set of data that is more manageable and more understandable. It's a way to find hidden patterns, show how those patterns overlap, and show what characteristics are seen in multiple patterns. It is also used to create a set of variables for similar items in the set. These sets of variables are called dimensions. It can be a very useful tool for complex sets of data involving psychological studies, socioeconomic status, and other involved concepts. A factor is a set of observed variables that have similar response patterns. They are associated with a hidden variable, called a confounding variable, that isn't directly measured. Factors are listed according to factor loadings, or how much variation in the data they can explain. The two types, exploratory and confirmatory. Exploratory factor analysis is if you don't have any idea about what structure your data is, or how many dimensions are in a set of variables. Is used for verification as long as you have a specific idea about what structure your data is, or how many dimensions are in a set of variables. Factor loadings. Not all factors are created equal. Some factors have more weight than others. In a simple example, imagine your bank conducts a phone survey for customer satisfaction, and the results show the following factor loadings. Multiple factor analysis. This subset of factor analysis is used when your variables are structured in variable groups. For example, you might have a student health questionnaire with several items like sleep patterns, addictions, psychological health, or learning disabilities. The two steps performed in multiple factor analysis are Principal component analysis is performed on each set of data. This gives an eigenvalue, which is used to normalize the datasets. The new datasets are merged into a unique matrix, and a second, global PCA is performed. Performing factor analysis. Factor analysis is an extremely complex mathematical procedure and is performed with software. What is confirmatory factor analysis? Confirmatory factor analysis allows a researcher to figure out if a relationship between a set of observed variables, also known as manifest variables, and their underlying constructs exists. It is similar to exploratory factor analysis. The main difference between the two is, if you want to explore patterns, use EFA. If you want to perform hypothesis testing, use CFA. EFA provides information about the optimal number of factors required to represent the dataset. With confirmatory factor analysis, you can specify the number of factors required. For example, CFA can answer questions like, does my 10-question survey accurately measure one specific factor? Although it is technically applicable to any discipline, it is typically used in the social sciences. Implementing confirmatory factor analysis. Perform a literature review to help you choose an appropriate model. For example, you might choose a diagram or equations. Determine if unique values are possible for the population parameter estimation. Collect your data. Perform initial data analysis to check for issues like missing data, collinearity, or outliers. Estimate the population parameters. Determine if the model you chose is working. If the model is unacceptable, consider performing explanatory factor analysis. And finally, interpret your results. What is exploratory factor analysis? Exploratory factor analysis, or EFA, is used to find the underlying structure of a large set of variables. It reduces data to a much smaller set of summary variables. EFA is almost identical to confirmatory factor analysis, CFA. Both techniques can, perhaps surprisingly, be used to confirm or explore. Similarities are: assess the internal reliability of a measure, examine factors or theoretical constructs represented by item sets. They assume the factors aren't correlated. Investigate the quality of individual items. There are, however, some differences, mostly concerning how factors are treated and used. EFA is basically a data-driven approach, allowing all items to load on all factors, while with CFA, you must specify which factors to load. EFA is a good choice if you don't have any idea about what common factors might exist. EFA can generate a large number of possible models for your data, something that may not be possible if a research has to specify factors. If you do have an idea of what the models look like, and you want to test your hypothesis about the data structure, CFA is a better approach. What is generalized Procrustes analysis, or GPA? Procrustes analysis is a way to compare two sets of configurations, or shapes. Originally developed to match two solutions from factor analysis, the technique was extended to generalized Procrustes analysis so that more than two shapes could be compared. The shapes are aligned to a target shape or to each other. GPA uses geometric transformations, for example, isotopic rescaling, reflection, rotation, or translation, of matrices to compare the sets of data. Use in sensory profiling. Generalized Procrustes analysis is a way to find an underlying structure in sensory profiling, which falls into two categories: conventional profiling and free choice profiling. With conventional profiling, a fixed set of descriptive terms is provided for the assessors. The assessors are usually highly trained individuals. For example, you could ask 3 experts their opinions on the body, scent, and taste of 4 brands of wine. The fixed descriptions might include crisp, angular, and buttery. The results can be averaged, so it's possible to use factor analysis or primary component analysis as well as GPA, to analyze the test. Free choice profiling gives respondents the freedom to answer questions in their own descriptive terms. As there are no fixed terms to average, it's not possible to use factor analysis or PCA. Case sets methods, like PCA, are used on this type of free choice profiling. The categories are the dimensions of generalized Procrustes analysis. Ideally, the number of dimensions is equal across the board. In this example, that would mean the expert gave a rating in all 3 areas. However, it is possible to run a generalized Procrustes analysis using unequal dimensions. What are latent variables? A latent variable, or hidden variable, is generally thought of as a variable that is not directly measurable or observable. For example, a person's level of neurosis, conscientiousness, or openness is all latent variables. Although you can't see these underlying variables, they aren't part of an experiment's dataset, they can cause effects on your experimental results. Latent variables are also known as constructs or hypothetical constructs, factors, hidden variables, hypothetical variables, true scores, unmeasured variables, unobserved variables. Text and image analysis. Similarities and differences between texts and images. Both are major communication mediums that were once very closely related. In fact, early written languages could be seen as a form of imagery. Also, in the modern day, both are found in abundance, nowhere more so than on the Internet. Separately on the likes of Flickr or forums, but more often together on platforms like Instagram, Twitter, Facebook, and news sites, each with varying degrees of text-to-image ratio. It almost hurts to try and visualize any of these concepts with an image, but the textual description does a pretty good job at giving you a general idea about them, to say the least. While the text does a much better job of describing concepts and expressing thoughts or feelings, images are sometimes easier and more efficient to produce, and, in some cases, they are a more appropriate and effective way to express yourself. The truth is, you can capture a lot of the simple facts and events in your surroundings with a single image, and with minimal effort compared to text. Simply point your phone's camera at something, and with a single tap, you've captured and shared the moment with the entire world. Text and image analysis. While text and images differ in many ways and can exist independently, they are in fact complementary and non-competing communication mediums. And to get a holistic view of the world, we would need to analyze both. Understanding images are as important as understanding text, as together they provide a more accurate picture of reality. From an AI perspective, this means we need hybrid systems that are not only capable of understanding both mediums, but are also able to discover links between the two and leverage those links to enhance the overall performance and accuracy of such analysis systems. Word clustering. Word clustering is a technique for partitioning sets of words into subsets of semantically similar words, and is increasingly becoming a major technique used in a number of NLP tasks, ranging from word sense or structural disambiguation to information retrieval and filtering. In literature, 2 main different types of similarity have been used, which can be characterized as follows. First, paradigmatic or substitutional similarity. 2 words that are paradigmatically similar may be substituted for one another in a particular context. For example, the word book can be replaced by magazine with no violation of the semantic well-formedness of the sentence, and therefore the 2 words could be said to be paradigmatically similar. Second, syntagmatic similarity. 2 words that are syntagmatically similar significantly occur together in text. For instance, cut and the knife, syntagmatically similar since they typically co-occur within the same context. Hereafter, we will refer to type 1 similarity as semantic similarity, while referring to type 2 similarity as more loosely as semantic relatedness. As we will see, The two aspects are obviously interconnected, and, in fact, they are often not kept apart in the literature, although we find it useful for classificatory purposes to maintain the distinction. Both types of similarity, computed through different methods, are used in the framework of a wide range of NLP applications. Survey of approaches. The methods and techniques for clustering words that we will consider here will be parted according to the kind of similarity they take into account: semantic similarity or semantic relatedness. Semantic similarity. Typically, semantic similarity is computed either on the basis of taxonomical relationships such as hyperonymy and synonymy, or through distributional evidence. The former approach presupposes prior availability of independent, hierarchically structured sources of lexicosemantic information, such as WordNet. With the latter approach, the semantic similarity between the two words W1 and W2 is computed on the basis of the extent to which their typical contexts of use overlap. The notion of taxonomy-based semantic similarity crucially hinges on words' membership of more general semantic classes. By contrast, distributionally based semantic similarity rests on the assumption that words entering into the same syntagmatic relation with the other words can be seen as semantically similar, although in this case the similarity may be grounded on covert properties orthogonal to their general semantic superclass. Semantic relatedness. Two words can be considered to be semantically related if they typically co-occur within the same context. In the section on distributionally based semantic similarity, we showed that word co-occurrence patterns are instrumental for identifying clusterings of semantically similar words. In this section, word co-occurrence patterns will be considered as such together with their first use for the resolution of a number of NLP problems. NLP applications using word clustering techniques. The various word clustering techniques described so far have a large number of potentially important applications, including helping lexicographers in identifying normal and conventional usage, helping computational linguists in compiling lexicons with lexicosemantic knowledge, providing disambiguation cues for parsing highly ambiguous semantic structures, such as noun compounds, complex coordinated structures, complements attachment, subject-object assignment for languages like Italian, sense identification, retrieving text and/or information from large databases, constraining the language model for speech recognition and optical character recognition to help disambiguate among phonetically or optically confusable words. Clustering application. Clustering depends critically on density and distance, or similarity, but these concepts become increasingly more difficult to define as dimensionality increases. In this paper, we offer definitions of density and similarity that will work well for high-dimensional data, actually for data of any dimensionality. In particular, we use a similarity measure that is based on the number of neighbors that 2 points share, and define the density of a point as the sum of similarities of a point's nearest neighbors. We then present a new clustering algorithm that is based on these ideas. This algorithm eliminates noise, or low-density points, and builds clusters by associating non-noise points with representative or core points, or high-density points. This approach handles many problems that traditionally plague clustering algorithms, for example, finding clusters in the presence of noise and outliers, and finding clusters in data that has clusters of different shapes, sizes, and density. We have used our clustering algorithm on a variety of high and low-dimensional datasets with good results. But in this paper, we present only a couple of examples involving high-dimensional datasets. Word clustering and time series derived from NASA Earth science data. A new shared nearest neighbor clustering algorithm and its applications. Clustering refers to running an application in multiple worker processes, or workers, all receiving requests on the same port. When Strong Loop Process Manager, or PM, runs an application, it automatically runs it in a cluster with a number of workers equal to the number of CPU cores on the system. When you deploy an application with Arc, you can run the application in a multi-process cluster. Simply enter the number of processes to run in the Build and Deploy module. If any one process in a cluster is terminated or dies due to an application error, Strong Loop Process Manager automatically starts up another process and attaches it to the cluster without having to restart the application, thus providing zero application downtime. If you inadvertently push a faulty deployment to a cluster, Strong Loop PM ensures rolling restarts. If the first process being restarted crashes, then the deployment is not pushed out to the remaining processes in the cluster. You can control application clusters with Arc and with SLC. Clustering and classifying documents. Document classification, or document categorization, is a problem in library science, information science, and computer science. The task is to assign a document to one or more classes or categories. This may be done manually, or intellectually, or algorithmically. The intellectual classification of documents has mostly been the province of library science, while the algorithmic classification of documents is mainly in information science and computer science. The problems are overlapping, however, and there is, therefore, interdisciplinary research on document classification. The documents to be classified may be texts, images, music, etc. Each kind of document possesses its special classification problems. When not otherwise specified, text classification is implied. Documents may be classified according to their subjects or according to other attributes, such as document type, author, printing year, etc. In the rest of this paper, only subject classification is considered. There are two main philosophies of subject classification of documents: the content-based approach and the request-based approach. Document clustering involves the use of descriptors and descriptor extraction. Descriptors are sets of words that describe the contents of a cluster. Document clustering is generally considered to be a centralized process. Examples of document clustering include web document clustering for search users. The application of document clustering can be categorized into two types: online and offline. Online applications are usually constrained by efficiency problems when compared to offline applications. Text clustering may be used for different tasks, such as grouping similar documents, like news, tweets, etc., and the analysis of customer or employee feedback, discovering meaningful implicit subjects across all documents. In general, there are two common algorithms. The first one is the hierarchical-based algorithm, which includes single link, complete linkage, group average, and Ward's method. By aggregating or dividing, documents can be clustered into a hierarchical structure, which is suitable for browsing. However, such an algorithm usually suffers from efficiency problems. The other algorithm is developed using the k-means algorithm and its variants. Generally, hierarchical algorithms produce more in-depth information for detailed analysis, while algorithms based around variants of the k-means algorithm are more efficient and provide sufficient information for most purposes. These algorithms can further be classified as hard or soft clustering algorithms. Hard clustering computes a hard assignment. Each document is a number of exactly one cluster. The assignment of soft clustering algorithms is soft. A document's assignment is a distribution over all clusters. In a soft assignment, a document has fractional membership in several clusters. Clustering in search engines. A web search engine often returns thousands of pages in response to a broad query. making it difficult for users to browse or to identify relevant information. Clustering methods can be used automatically to group the retrieved documents into a list of meaningful categories, as is achieved by open-source software. Procedures. In practice, document clustering often takes the following steps. First, tokenization. Tokenization is the process of parsing text data into smaller units, or tokens, such as words and phrases. Commonly used tokenization methods includes bag of words model and n-gram model. Second, stemming and lemmatization. Different tokens might carry out similar information, for example, tokenization and tokenizing, and we can avoid calculating similar information repeatedly by reducing all tokens to its base form using various stemming and lemmatization dictionaries. Third, removing stop words and punctuation. Some tokens are less important than others. For instance, common words such as "the" might not be very helpful for revealing the essential characteristics of a text. So usually, it is a good idea to eliminate stop words and punctuation marks before doing further analysis. Fourth, computing term frequencies, or if-idf. After pre-processing the text data, we can then proceed to generate features. For document clustering, one of the most common ways to generate features for a document is to calculate the term frequencies of all its tokens. Although not perfect, these frequencies can usually provide some clues about the topic of the document. And sometimes it is also useful to weight the term frequencies by the inverse document frequencies. See if-idf for detailed discussions. Fifth, clustering. We can then cluster different documents based on the features we have generated. See the algorithm section in cluster analysis for different types of clustering methods. And sixth, evaluation and visualization. Sentiment analysis. A definition of sentiment analysis. Sentiment analysis is a method for gauging opinions of individuals or groups, such as a segment of a brand's audience, or an individual customer in communication with a customer support representative. Based on a scoring mechanism, sentiment analysis monitors conversations and evaluates languages and voice inflections to quantify attitudes, opinions, and emotions related to a business, product, service, or topic. Sentiment analysis is sometimes also referred to as opinion mining. How sentiment analysis works. Sentiment analysis is often driven by an algorithm, scoring the words along with voice inflections that can indicate a person's underlying feelings about the topic of a discussion. Sentiment analysis allows for a more objective interpretation of factors that are otherwise difficult to measure or typically measured subjectively, such as the amount of stress or frustration in a customer's voice, how fast the individual is speaking or rate of speech, changes in the level of stress indicated by the person's speech, such as in response to a solution provided by a customer support representative. In customer service and call center applications, sentiment analysis is a valuable tool for monitoring opinions and emotions among various customer segments, such as customers interacting with a certain group of representatives during shifts, customers calling regarding a specific issue, product or service lines, and other distinct groups. Sentiment analysis may be fully automated, based entirely on human analysis, or some combination of the two. In some cases, sentiment analysis is primarily automated, with a level of human oversight that fuels machine learning, and helps to refine algorithms and processes, particularly in the early stages of implementation. Examples of sentiment analysis. Sentiment analysis is used across a variety of applications and for myriad purposes. For instance, sentiment analysis may be performed on Twitter to determine overall opinion on a particular trending topic. Companies and brands often utilize sentiment analysis to monitor brand reputation across social media platforms or across the web as a whole. One of the most widely used applications for sentiment analysis is for monitoring call center and customer support performance. As companies seek to keep a finger on the pulse of their audience, sentiment analysis is increasingly utilized for overall brand monitoring purposes. Sentiment analysis has been used by political candidates and administrations to monitor overall opinions about policy changes and campaign announcements, enabling them to fine-tune their approach and messaging to better relate to voters and constituents. In brand reputation management applications, overall trends in sentiment analysis enable brands to identify peaks and valleys in overall brand sentiment or shifts in attitudes about products or services, thus enabling companies to make improvements perfectly in tune with customer demands. Benefits of sentiment analysis. A relative sentiment analysis score provides insight into the effectiveness of call center agents and customer support representatives, and also serves as a useful measurement to gauge the overall opinion on a company's products or services. When sentiment analysis scores are compared across certain segments, companies can easily identify common pain points, areas for improvement in the delivery of customer support, and overall satisfaction between product lines or services. By monitoring attitudes and opinions about products, services, or even customer support effectiveness continuously, brands are able to detect subtle shifts in opinions and adapt readily to meet the changing needs of their audience. Challenges and best practices for sentiment analysis. Language is complex, and as a process for quantifying and scoring language, sentiment analysis is equally complex. What is relatively easy for humans to gauge subjectively in face-to-face communication, such as whether an individual is happy or sad, excited or angry about the topic at hand, must be translated into objective, quantifiable scores that account for the many nuances that exist in human language, particularly in the context of a discussion. For instance, a word that otherwise carries a positive connotation used in a sarcastic manner could easily be misinterpreted by an algorithm if both context and tone are not taken into consideration. Given these challenges, sentiment analysis solutions must consider acoustic measurements, such as the rate of speech, stress in a caller's voice, and changes in stress signals, in the context of the conversation. Additionally, integrating machine learning into the mix enables sentiment analysis to become more accurate over time, as algorithms learn and adapt to the commonalities in conversations, and how the context of conversations can change outcomes. In call center and customer support applications, sentiment analysis that operates in real time provides crucial feedback to agents and representatives, allowing them to respond appropriately to impact the outcome of the interaction. When used in conjunction with powerful features like semantic building blocks, companies can easily monitor agent performance by identifying positive patterns such as frustration or dissatisfaction in the early stages of a call, followed by positive sentiments in the latter portion of the call, representing an agent's ability to talk down frustrated customers. When utilizing the right technology tools and applying it to key business drivers, sentiment analysis is a powerful tool for steering companies and their individual business units to successful outcomes from every customer interaction. Defect prediction model, a boon to business enterprises. According to a recent research, 40% of the companies reported failed software schedule and budget estimation, while only 14% reported good performance. In yet another research conducted by Dynamic Markets Limited, 62% of the organizations experienced IT projects that failed to meet their schedules, while 49% experienced budget overruns. Most of the enterprises, IT or non-IT, are suffering gigantic losses due to poor estimations. The losses are reported to be as huge as a few millions of dollars to $1 billion in some cases. These losses could have been avoided if a good prediction model had been used. A sophisticated prediction model helps you identify the vulnerabilities in your project plan in terms of insufficient resources, poor timelines, predictable defects, etc. It has been realized that the project estimations for smaller projects are more accurate as compared to large complex ones. The reasons can be numerous, right from the involvement of huge resources to varying requirements. Recent trends show that the organization's focus has shifted from defect detection to defect prevention approach. Though not many organizations have explored any such model, few of the testing vendors have already started paving its way toward such prediction models. This model forecasts the defect trends earlier, identifies the schedule variation, improves the efficiency of the testing phase, and helps enterprises stick to delivery schedule by taking informed decisions on budgeting, QA best practices, and resource allocation. Such model uses a step-by-step approach towards identifying and analyzing different data parameters based on various algorithms and statistical models to predict the defect. Based on the output of such statistical analysis, the scheduled and actual pace of any project can be compared, and the variation, if any, can be determined. On having any such variations, you can actually plan for the next set of corrective actions in order to bring the project back on track, thus eliminating the cause. Though difficult to believe, such prediction models can help you realize 95% precision between actual and predicted defects. How prediction model works. Historical data plays a prominent role to assess the defect inflow trends and the past deviations from the schedule variation. All defects will not have the same impact on the functionality, product, or service, and hence, more effort should be allocated towards the defects that will have a higher impact on the deliverables. In a similar way, different parameters such as team size, the total number of features, tasks completed, testing effort, number of test cases, release complexity, and so on, will have a different bearing on the defects. Thus, identifying the key parameters which can influence the defects is of utmost importance. These parameters, thus identified, are then used for further analysis. Data quality plays a crucial role in the overall functionality of such models. Hence, you need to be very vigilant while selecting such data samples. A defect prediction model, if utilized correctly, can help your organization harvest huge profits without getting delayed on planned schedules or overrun on budget estimates. It helps you modify the parameters so as to meet the schedule variations. It can help you avoid any delays in the delivery schedules, but does not guarantee you the success. Prediction, being a difficult exercise, requires attention from senior executives as well in order to understand the technical implications and limitations from a business viewpoint. In this chapter, we will have a brief discussion about big data. Even if you show even a minute amount of interest in the technical aspects of the net and connective devices, you should be well aware of how humongous amounts of data are generated on a daily basis and owe their origins to several sources. And so it is necessary to have an analytics layer in order to make the best of all of the data that is available to us. Predictive analysis is only becoming more and more relevant, which promises to have a significant positive impact on businesses, as well as the bottom line. But the problem with predictive analysis lies in the fact that it is dependent on large sets of mathematical computations and is a process that requires large amounts of memory to be present. So, when we computationally deal with big data, performing mathematical computations on the same becomes even more difficult. So, we end up facing two particular predicaments. First, optimizing the process of computing for predictive analysis of big data in the presence of computational resources that are comparatively limited in scope. Second, figure out ways through which we may deal with huge amounts of data with memory that is limited. The solution to this particular challenge may be approached in two distinct ways. The Hadoop ecosystem, that taps into the power of parallel computing, and is considered by many to be the best solution that is available, especially so if one considers the fact that it is open source. Most of the practitioners in this field are well aware that Hadoop has its conceptual basis on cluster-based parallel computation and the distributed file system of Hadoop. If you intend to run a machine learning algorithm over the cluster of Hadoop, you need a thorough knowledge of MapReduce programming, and the learning curve is raised to even more difficult levels when you are not well acquainted with the intricacies of programming. In case your computational resources are limited to having only a single PC when using Hadoop, we will be unable to perform computational tasks on large datasets. So, in such circumstances, we should continually look for another solution. R and MySQL may together form another viable solution. We will now overcome the first obstacle that we mentioned above. In this case, through predictive analysis computations, we refer to the task of building a model of machine learning on the dataset. A machine learning model comprises of varied formulas of mathematics. Let us now venture into the intricacies of machine learning, the predictive model, and try to secure an understanding of the reason behind the increased computational difficulty of working with larger sets of data. A predictive model of a basic manifestation is created through the use of techniques of logistic and linear regression. Now, suppose we are in the process of creating a linear regression model. We face the following challenges. Data is so large that we are unable to load it into memory while using R programming. Even when we are able to load data into our memory, the memory that is left is most often insufficient to perform mathematical computations. Both the above scenarios require a unique solution that will ultimately let us process large data in R and perform calculations on the same data. Regression analysis basics. Regression analysis. Regression analysis allows you to model, examine, and explore spatial relationships, and can help explain the factors behind observed spatial patterns. Regression analysis is also used for prediction. You may want to understand why people are persistently dying young in certain regions, for example, or may want to predict rainfall where there are no rain gauges. OLS is the best known of all regression techniques. It is also the proper starting point for all spatial regression analysis. It provides a global model of the variable or process you are trying to understand or predict, such as early death or rainfall. It creates a single regression equation to represent that process. Geographically weighted regression, or GWR, is one of the spatial regression techniques, increasingly used in geography and other disciplines. GWR provides a local model of the variable, or process you are trying to understand or predict, by fitting a regression equation to every feature in the dataset. When used properly, these methods are powerful and reliable statistics for examining or estimating linear relationships. Linear relationships are either positive or negative. If you find that the number of search and rescue events increases when daytime temperatures rise, the relationship is said to be positive. There is a positive correlation. Another way to express this positive relationship is to say that search and rescue events decrease as daytime temperatures decrease. Conversely, if you find that the number of crimes goes down as the number of police officers patrolling an area goes up, the relationship is said to be negative. You can also express this negative relationship by stating that the number of crimes increases as the number of patrolling officers decreases. The graphic below depicts both positive and negative relationships, as well as the case where there is no relationship between the two variables. Correlation analysis and their associated graphics, depicted above, test the strength of the relationship between two variables. Regression analysis, on the other hand, make a stronger claim. They attempt to demonstrate the degree to which one of the variables potentially promotes positive or negative change in another variable. Using regression analysis. Regression analysis can be used for a large variety of applications. Modeling fire frequency to determine high-risk areas and to understand the factors that contribute to high-risk areas. Modeling property loss from fire as a function of variables such as the degree of fire department involvement, response time, property value, etc. If you find that response time is the key factor, you may need to build more fire stations. If you find that involvement is the key factor, you may need to increase equipment or officers dispatched. Modeling traffic accidents as a function of speed, road conditions, weather, etc., in order to inform policy aimed at decreasing accidents. There are 3 primary reasons you might want to use regression analysis: to model some phenomena in order to better understand it and, possibly, use that understanding to affect policy, or to make decisions about appropriate actions to take. Basic objective: to measure the extent that changes in one or more variables jointly affect changes in another. Example: understand the key characteristics of the habitat for some particular endangered species of bird, perhaps precipitation, food sources, vegetation, predators, to assist in designing legislation aimed at protecting that species. To model some phenomena in order to predict variables for that phenomenon at other places or other times. Basic objective: to build a prediction model that is consistent and accurate. Example: where are real estate values likely to go up next year? Or, there are rain gauges at particular places and a set of variables that explain the observed precipitation values. How much rain falls in places where there are no rain gauges? Regression may be used in cases where interpolation is not effective because of insufficient sampling. There are no gauges on peaks or in valleys, for example. You can also use regression analysis to test hypotheses. Suppose you are modeling residential crime in order to better understand it and, hopefully, implement a policy to prevent it. As you begin your analysis, you probably have questions or hypotheses that you want to test. Broken window theory indicates that defacement of public property, like graffiti, damaged structures, etc., invite other crimes. Will there be a positive relationship between vandalism incidents and residential burglary? Is there a relationship between illegal drug use and burglary? Might drug addicts steal to support their habits? Are burglars predatory? Might there be more incidents in residential neighborhoods with higher proportions of elderly or female-headed households? Is a person at greater risk for burglary if they live in a rich or a poor neighborhood? You can use regression analysis to test these relationships and answer your questions. Regression analysis components. It is impossible to discuss regression analysis without first becoming familiar with a few terms and basic concepts specific to regression statistics. Regression equation. This is the mathematical formula applied to explanatory variables in order to best predict the dependent variable you are trying to model. Unfortunately for those in the geosciences who think as x and y as coordinates, the notation in regression equations for the dependent variables is always y, and for independent or explanatory variables is always x. Each independent variable is associated with the regression coefficient, describing the strength and the sign of that variable's relationship to the dependent variable. Dependent variable, y. This is the variable representing the process you are trying to predict or understand. For example, residential burglary, foreclosure, or rainfall. In the regression equation, it appears on the left side of the equal sign. While you can use regression to predict the dependent variable, you always start with a set of known y values and use these to build or to calibrate the regression model. The known y values are often referred to as observed values. Independent or explanatory variables, x. These are the variables used to model or to predict the dependent variable values. In the regression equation, they appear on the right side of the equal sign and are often referred to as explanatory variables. We say that the dependent variable is a function of the explanatory variables. If you are interested in predicting annual purchases for a proposed store, you might include in your model explanatory variables representing the number of potential customers, distance to competition, store visibility, and local spending patterns, for example. Regression coefficients, beta. Coefficients are computed by the regression tool. They are values, one for each explanatory variable, that represent the strength and type of relationship the explanatory variable has to the dependent variable. Suppose you are modeling fire frequency as a function of solar radiation, vegetation, precipitation, and aspect. You might expect a positive relationship between fire frequency and solar radiation. The more sun, the more frequent the fire instance. When the relationship is positive, the sign for associated coefficient is also positive. You might expect a negative relationship between fire frequency and precipitation. Places with more rain have fewer fires. Coefficients for negative relationships have negative signs. When the relationship is a strong one, the coefficient is large. Weak relationships are associated with coefficients near zero. P-values. Most regression methods perform a statistical test to compute a probability, called a p-value, for the coefficients associated with each independent variable. The null hypothesis for this statistical test states that a coefficient is not significantly different from zero. In other words, for all intents and purposes, the coefficient is zero, and the associated explanatory variable is not helping your model. Small p-values reflect small probabilities and suggest that the coefficient is indeed important to your model, with a value that is significantly different from zero, or the coefficient is not zero. You would say that a coefficient with a p-value of 0.01, for example, is statistically significant at the 99% confidence level. The associated variable is an effective predictor. Variables with coefficients near zero do not help predict or model the dependent variable. They are almost always removed from the regression equation, unless there are strong theoretical reasons to keep them. Residuals. These are the unexplained portion of the dependent variable, represented in the regression equation as the random error term. Known values for the dependent variable are used to build and to calibrate the regression model. Using known values for the dependent variable y, and known values for all of the explanatory variables, the x's, the regression tool constructs an equation that will predict those known y values, as well as possible. The predicted values will rarely match the observed values exactly. The difference between the observed y values and the predicted y values are called the residuals. The magnitude of the residuals from a regression equation is one measure of model fit. Large residuals indicate poor model fit. Building a regression model is an iterative process that involves finding effective independent variables to explain the processes you are trying to model or understand, then running the regression tool to determine which variables are effective predictors, then removing or adding variables until you find the best model possible. Regression analysis issues. OLS regression is a straightforward model, has a well-developed theory behind it, and has a number of effective diagnostics to assist with interpretation and troubleshooting. OLS is only effective and reliable, however, if your data and regression model meets and satisfies all of the assumptions inherently required by this method. See the table below. Spatial data often violate the assumptions and requirements of OLS regression, and so it is important to use regression tools in conjunction with the appropriate diagnostic tools that can assess whether or not regression an appropriate method for your analysis, given the structure of the data and the model being implemented. Spatial regression. Spatial data exhibit two properties that make it difficult, but not impossible, to meet the assumptions and requirements of traditional, non-spatial statistical methods like OLS regression. Geographic features are more often than not spatially autocorrelated. This means that features near each other tend to be more similar than features that are far away. This creates an overcount type of bias for traditional, non-spatial regression methods. Geography is important, and often the processes most important to the model are non-stationary. These processes behave differently in different parts of the study area. This characteristic of spatial data can be referred to as regional variation, or spatial drift. True spatial regression methods were developed to be robust to these two characteristics of spatial data, and even to incorporate these special qualities of spatial data in order to improve their ability to model data relationships. Some spatial regression methods deal effectively with the first characteristic, spatial autocorrelation. Others deal effectively with the second, non-stationarity. At present, no spatial regression methods are effective for both characteristics. For a properly specified GWR model, however, spatial autocorrelation is typically not a problem. Classification tree analysis. Classification tree analysis, or CTA, is a type of machine learning algorithm used for classifying remotely sensed and ancillary data in support of land cover mapping and analysis. A classification tree is a structural mapping of binary decisions that lead to a decision about the class, or interpretation, of an object, such as a pixel. Although sometimes referred to as a decision tree, it is more properly a type of decision tree that leads to categorical decisions. A regression tree, another type of decision tree, leads to quantitative decisions. A classification tree is composed of branches that represent attributes, while the leaves represent decisions. In use, the decision process starts at the trunk and follows the branches until a leaf is reached. The figure above illustrates a simple decision tree based on a consideration of the red and infrared reflectance of a pixel. Classification tree analysis, CTA, is an analytical procedure that takes examples of known classes, for example, training data, and constructs a decision tree based on measured attributes such as reflectance. In Tairset, the CTA model is based on the C4.5 algorithm. In essence, the algorithm iteratively selects the attribute, such as reflectance band, and value that can split a set of samples into two groups, minimizing the variability within each subgroup while maximizing the contrast between the groups. 4 key advantages of using decision trees for predictive analytics. We have demonstrated a couple of applications of using decision trees with open-source analytics packages such as RapidMiner. There are several distinct advantages of using decision trees in many classification and prediction applications. Some vendors prefer names such as classification and regression trees, CART or C&RT, but they still refer to the same analytics technique at the core. Keep the following factors in mind while considering them for your business analytics applications. Advantage 1. Decision trees implicitly perform variable screening, or feature selection. We described here why feature selection is important in analytics. We also introduced a few common techniques for performing feature selection or variable screening. When we fit a decision tree to a training dataset, the top few nodes on which the tree is split are essentially the most important variables within the dataset, and feature selection is completed automatically. Advantage 2. Decision trees require relatively little effort from users for data preparation. To overcome scale differences between parameters, for example, if we have a dataset which measures revenue in millions and loan age in years, say, this will require some form of normalization or scaling before we can fit a regression model and interpret the coefficients. Such variable transformations are not required with decision trees because the tree structure will remain the same with or without the transformation. Advantage 3. Nonlinear relationships between parameters do not affect tree performance. As we described here, highly nonlinear relationships between variables will result in failing checks for simple regression models, and thus make such models invalid. However, decision trees do not require any assumptions of linearity in the data. Thus, we can use them in scenarios where we know the parameters are non-linearly related. Advantage 4. The best feature of using trees for analytics: easy to interpret and explain to executives. Decision trees are very intuitive and easy to explain. Just build one and see for yourself. These advantages need to be tempered with one key disadvantage of decision trees. Without proper pruning or limiting tree growth, they tend to overfit the training data, making them somewhat poor predictors. About trees classified as evergreen. What sort of evergreen do you think is best suited for your neighborhood climate? There's a lot to consider, but once you have a basic understanding of how to properly classify evergreens, you'll discover just how plentiful, robust, and charming these trees really are. Evergreens have that holiday charisma in many homes, but there is a multitude of uses for this tree. In fact, it's important to understand a little about how evergreens are classified to understand their usefulness. The most important classification method has been standardized among botanists for centuries. All living organism is divided into a few kingdoms. For evergreen, they are in the Platia kingdom. The kingdom is further divided into phyla, or phylum, to help organize similar plants into groups. Phylum include plants with somewhat distinct differences, so further subcategorization was necessary. Phyla are organized into classes. Each class is then divided into orders and then into families. To classify a tree such as an evergreen, distinct characteristics need to be determined. Evergreen trees come in a variety of shapes and sizes, with varying colors, needle structures, and a desire for particular soil bases. Evergreens, just as many other trees, owning up to a specific plot of real estate, be it in a forest, a subdivision, or other landscape of varying features and attributes, desire preferential treatment. If evergreens could bark, you might hear them howling at the skies, stating they have a preference for certain climates. The spruce is one of the most famously planted evergreens. Spruce trees develop short, sharp needles that vary from 1 to 2 inches in length. The color of the foliage ranges from a rich dark green to a strong hardy blue. Of all the spruce varietals, one of the most popular forms of the spruce tree is the Colorado spruce. In the past, they were known as the Colorado blue. Someone somewhere along the way removed the blue from its name. The Colorado spruce takes its fame to new heights, growing to an average of 40 to 60 feet tall, with a width of up to 30 feet at its base. This cone-shaped beauty is not shy. Colorado vibrates in dark green needles for all to see. The Black Hill spruce, another common variety of evergreen, has much darker foliage, with finer needles in comparison to Colorado. The Black Hill tree grows on average 30 to 40 feet tall, with a 20 to 30 foot width. Again, the basic cone shape is present in this spruce as well. All pines have needles that grow in bundles. The needle's length ranges from 1 to 3 inches long. Varieties well fit to colder climates include the following trees: white, red or Norway, Scotch, and Swiss stone. Remember, when classifying evergreens, there is an organized format, one that has been followed for centuries. This organization makes it possible to breed evergreens, understand their growth cycles, and helps people determine whether or not a specific evergreen is suitable for a specific plot of land. Evergreens are beautiful, robust trees with a variety of uses. Bayes nets. A Bayesian network is a graphical model that encodes probabilistic relationships among variables of interest. When used in conjunction with statistical techniques, the graphical model has several advantages for data analysis. 1. Because the model encodes dependencies among all variables, it readily handles situations where some data entries are missing. 2. A Bayesian network can be used to learn causal relationships, and hence can be used to gain an understanding of a problem domain, and to predict the consequences of intervention. 3. Because the model has both a causal and probabilistic semantics, it is an ideal representation for combining prior knowledge, which often comes in causal form, and data. 4. Bayesian statistical methods, in conjunction with Bayesian networks, offer an efficient and principled approach for avoiding the overfitting of data. In this paper, we discuss methods for constructing Bayesian networks from prior knowledge and summarize Bayesian statistical models for using data to improve this model. With regard to the latter task, we describe methods for learning both the parameters and structure of a Bayesian network, including techniques for learning with incomplete data. In addition, we relate Bayesian network methods for learning to techniques for supervised and unsupervised learning. We illustrate the graphical modeling approach using a real-world case study. Bayes nets, or Bayesian networks, give remarkable results in determining the effects of many variables on an outcome. They typically perform strongly, even in cases where other methods falter or fail. These methods have had relatively little use with business-related problems, although they have worked successfully for years in fields such as scientific research, public safety, aircraft guidance systems, and national defense. Bayes nets fully warrant wider use. Importantly, they often outperform regression, particularly in determining variables' effects. Regression is one of the most august multivariate methods, and among the most studied and applied. However, it has some properties that make it less than ideal for determining the strength of variables in influencing outcomes. Let's go over a small example, and then talk about some properties of networks that lead to their typically strong performance. How Bayes nets work. As the term network implies, connections form between the variables based on how they most closely align across their distributions, or patterns of variables. Variables closest to each other have the strongest similarities in these patterns. Variables being in a network also mean that they all influence one another. A change in one affects all other variables. Variables closest to each other have the most influence on each other. This pattern of effects has been compared to ripples moving across a disturbance in a pond. Movements are largest at points closest to whatever caused the ripples, and there is some movement, even if slight, at all points. Networks can be self-assembling, finding the best pattern of connections to explain or predict the target variable. They learn the structures of the data, looking for the strongest connections. In the word association analysis, we made a target-centered net, so that all variables connected with the target, or purchase intent, but otherwise they connected to each other based solely on patterns in the data. Using conditional probability gives Bayes nets strong analytical advantages over traditional regression-based models. This adds to several advantages we discussed in an earlier chapter. These include all variables interconnecting. Any change in one variable takes into account how that variable relates to all others. This is a basic property of networks. In regressions, any change assumes that all other variables remain constant. That works perfectly with a controlled experiment, but rarely so in real life, where we find many subtle connections. A whole distribution view of data. The entire distribution of variables' values enters the analysis. All regression-based models rely on correlations. A correlation is a one-number summary of how well two variables align in a straight line. Ability to handle many variables. Working Bayes nets with over 2,000 variables have been reported in scientific chapters. These provide accurate predictions and readings of effects. This differs from regression, where the apparent effects of variables shrink as more are added to the model. In fact, in regression, the coefficient or effect of any given variable in a model may be influenced more by the presence of other variables in the model than any underlying relationship with the target or dependent variable. But what is conditional probability, and what makes it different? In short, conditional probability means that the effects of one variable depend on, or flow from, the distribution of the other variable, or others. The complete state of one variable determines how another acts. This likely sounds opaque, so let's see how this works. This is a small example of conditional probability that you can see in more detail in Practical Text Analytics, Strohl, 2015. The initial problem comes from the work of Kahneman and Iversky, 1982. The taxicab problem. Suppose there is a city with just yellow and white cabs. Some 85% of the cabs are yellow, and the rest white. An accident occurs, and a witness says the cab is white. He proves to be 80% correct at identifying each color cab. If he says the cab is white, what are the odds the cab is truly white? Most people guess either 12% or 80%. Some try a cleverer saming approach and say 80% times 80% or 64%. But all these answers are quite wrong. Bayes nets immediately see the correct answer. It is, 41.4%. How can nearly all of us be so wrong? And how can Bayes nets solve this easily? To show how this works, we will need to make our own tiny network. While networks can self-assemble from patterns in the data, we also can make them by hand to solve specific problems. This network is as small as possible, linking two variables, the color of the cab and what the witness reports as the color. Each variable is called a node. Developing Bayesian networks based on text mining. Bayesian network is a widely used tool for data analysis, modeling, and decision support in various domains. There is a growing need for techniques and tools which can automatically construct Bayesian networks from massive text or literature data. In practice, Bayesian networks also need to be updated when new data is observed, and literature mining is a very important source of new data after the initial network is constructed. Information closely related to a Bayesian network usually includes the causal associations, statistics information, and experimental results. However, these associations and numerical results cannot be directly integrated with the Bayesian network. The source of the literature and the perceived quality of research needs to be factored into the process of integration. In this demo, we will present a general methodology and toolkit called AutoBayesian that we developed to automatically build and update a Bayesian network based on the causal relationships derived from text mining. An experiment on using Bayesian networks for process mining. Process mining is a technique that performs an automatic analysis of business processes from a log of events, with the promise of understanding how processes are executed in an organization. Several models have been proposed to address this problem. However, here we propose a different approach to deal with uncertainty. By uncertainty, we mean estimating the probability of some sequence of tasks occurring in a business process, given that only a subset of tasks may be observable. In this sense, this work proposes a new approach to perform process mining using Bayesian networks. These structures can take into account the probability of a task being present or absent in the business process. Moreover, Bayesian networks are able to automatically learn these probabilities through mechanisms such as the maximum likelihood estimate and EM clustering. Experiments made over a loan application case study suggest that Bayesian networks are adequate structures for process mining and enable a deep analysis of the business process model that can be used to answer queries about that process. Term extraction. The first step is to transform any unstructured data into structured data. This can be performed during a pre-processing stage along with other tasks, such as data cleansing. In this example, we want to extract key terms from the purpose column, which can contain free-form text. To do this, we can use a term extraction tool. Many such tools exist, such as Stanford NLP, OpenNLP, or Microsoft SQL Server Integration Services, or SSIS, which has transformations called term extraction and term lookup. Learning. In order to learn the text classification model from data, we need to map columns of data to variables. The data above is currently contained in two tables, so there is not a one-to-one correspondence between a column of data and a variable in the model. We can proceed in one of the following ways. Flatten the data after the term extraction process, such that we have a column for each term containing the score. Use the Bayes server API, mapping the terms and their scores to variables using code. Inference. Once we have built our classification model, we can perform inference or predictions in the usual way on unseen data. In other words, data that does not include the risk, as that is what we are trying to predict. As with learning, data will need to be flattened or applied using the Bayes Server API. Sequences. Since Bayes Server supports time series and sequence models, if necessary, we can also model sequences of terms such as sequence of terms within a particular line of text and the evolution of text in time. 5. Bayesian network software. AgenaRisk. AgenaRisk Bayesian network software is targeted at modeling, analyzing, and predicting risk through the use of Bayesian networks. It has a surprisingly large number of big brand users in aerospace, banking, defense, telecom, and transportation. 2 free versions are available, one subject to buying a book, but both are throttled to model size. AgenaRisk Pro is available through subscription, and AgenaRisk Enterprise provides support for enterprise deployment of models. Bayesian. Bayesian Labs supports the creation of Bayesian networks with good graphical capabilities and a relatively gentle learning curve. Bayesian Market Simulator allows the analysis of a competing set of offers in relation to a defined population. Integration with applications is achieved through Bayesian engines, and Bayesian Graph Layout Engine supports the positioning of graphs in other applications. Bayes Server. Bayes Server features a functional graphical user interface and a rich set of tools for diverse Bayesian analysis tasks, dynamic Bayesian networks for time series, multiple variable nodes, relevance optimization, and many others. It is used for classification, regression, time series prediction, clustering, and most forms of data mining tasks. It runs in a Windows environment, and the Express Edition comes in at £388 and the Professional Edition at £1,297. A server version is also available for multiple users. Designed. This is a knowledge-based system using Bayesian network software and has applications in the contact center, customer self-service, and knowledge base administration. A number of products are built around the Bayesian network capability, including a contact center portal, self-service portal, offline troubleshooter, virtual assistant, and other automated advisory modes. Netica. Netica from Norsis is claimed to be the most widely used Bayesian network development software. The graphical user interface supports belief networks and influence diagrams, giving a very visual approach to Bayesian analysis. The commercial edition costs $585 and the personal edition $285. A free version is available, which is limited in the model size it supports. 10 free and open source Bayesian network software. Banjo, or Bayesian Network Inference with Java Objects. Static and Dynamic Bayesian Networks. Bayesian Network Tools in Java, or BNJ, for research and development using graphical models of probability. It is implemented in 100% pure Java. Bugs. Bayesian inference using Gibbs sampling. Bayesian analysis of complex statistical models using Markov chain Monte Carlo methods. dlib C++ library, with extensive Bayesian network support. Dynamic Bayesian network simulator. FBN, free Bayesian network for constraint-based learning of Bayesian networks. Java Bayes is a system that calculates marginal probabilities and expectations, produces explanations, performs robustness analysis, and allows the user to import, create, modify, and export networks. JBNC is a Java toolkit for training, testing, and applying Bayesian network classifiers. JNCC2 is the Java implementation of the native Creedle classifier 2. MSBNX is a component-based Windows application for creating, assessing, and evaluating Bayesian networks. SMILE, Structural Modeling, Inference, and Learning Engine, is a fully portable library of C++ classes implementing graphical decision theoretic methods such as Bayesian networks and influence diagrams. UnBayes, framework and GUI for Bayes nets and other probabilistic models. Thanks again for buying my book. If you have a minute, please leave a review. I take reviews seriously and always look at them. This way, you are helping me provide you better content that you will love in the future. A review doesn't have to be long, just 1 or 2 sentences and a number of stars you find appropriate. Hopefully 5, of course. Also, if I think your review is useful, I will mark it as helpful. This will help you become more known on Amazon as a decent reviewer, and will ensure that more authors will contact you with free ebooks in the future. This is how we can help each other. You can look at these books too: Data Analytics, Data Mining, and Data Science for Business. Disclaimer: this information is provided as is. The author, publishers, and/or marketers of this information disclaim any loss or liability, either directly or indirectly as a consequence of applying the information provided herein, or in regard to the use and application of said information. No guarantee is given, either expressed or implied, in regard to the merchantability, accuracy, or acceptability of the information. The pages within this ebook have been copyrighted. This has been Text Analytics: Practical Steps to Sort Data. Written by David Feldspar. Narrated by Jason R. Gray. Copyright 2018 by David Feldspar. Production copyright 2018 by David Feldspar.